So this is our second video on properties of logarithms, and in this one, as I said, we're going to go over several examples using the properties of logarithms. Now just to remember here, I'll write down the properties here in this video that we're going to be using. We have the change of base, which we probably won't be using in this video. We did a couple examples of that in the last video. Change of base, but just to remind you, this is saying that log base a of x is equal to log base b of x divided by log base b of a. So this again allowed us to compute any logarithm using our calculator because we could use either the common log or the natural log. But then we had three other log properties, and there was the product property, and that was if you had the log base a of m times n, this was equal to the log base a of m plus the log base a of n. And we actually proved this, and I would encourage you not only to go back and view the proof to make sure you understand it, but then also see if you could do the proof for the subtraction one, because we didn't do that one, but sometimes we do put proof of this on an exam. So then we also had the quotient one, and this was if you have log base a of m divided by n, this was simply log base a of m minus log base a of n. And then we had the power property, and this was if we had the log base a of capital M to the little n power, and I mean you can put it in parentheses if you want to. I like to do that often because it reminds me that the log base a is a function, so you do everything inside the parentheses first, then you would do the logarithm. And so this, though, the property says that instead of having that exponent there, we could bring n, the little n, down and have n times log base a of just m. Alright, so we're going to do an example here using some of these. A pretty straightforward example here to start with. So we're going to do here, let's see here, write the following logarithms in terms, trying to give a little bit of space there, in terms of log base 3, so the common log base 3, and the common log base 5. And so what we're going to have here is we're going to have the log of 75 is the first one we're going to look at. And so if we think about this, the log of 75, this is simply just equal to, well, we want 3 and 5, so this is equal to the log of 3 times 25, which this is then equal to the log of 3 times 5 squared. So now I've got 3 and 5 there. Now I'm going to apply my log properties. Now I'm first going to apply the product property. So this would be equal to log of 3 plus the log of 5 squared. Now I said log of 5, not log of 5 squared, so I'm going to use the property of the power one, and we get a final answer here of log of 3 plus 2 log of 5. Now, you can verify this on a calculator. You can do the log of 75 and get a number. In fact, if you do the log of 75, you get 1.875 going on forever. And then you could do the log of 3 plus 2 times log of 5, and you should get the same answer. And just I'll do it here without writing it down on my calculator. And yes, you get the exact same answer, which we shouldn't be surprised because of the log properties. Now, some of you might say, well, why would I ever use these log properties or write it down in this last line here? Why wouldn't I just compute the log of 75? And you're right, with numbers, we really wouldn't do that. But this is just to get us practice using the properties, because we'll use the properties when we have algebraic expressions, and we'll use them there as well as when trying to solve equations. Which will be in the next set of videos here. So this is just to start us getting practicing on these log properties. It's not so much, oh, this is stuff we'll do on a regular basis. So let's look at one more example with the log of 3 and log of 5. So this would be part B. And for this, we're going to look at the log of 9 over 125. Now, we're wanting to do this and do the same thing, express this in terms of log of 3 and log of 5. So the first thing we should do is rewrite this as the log, and then think of, well, what is 9? Well, 9 is 3 squared, and then what is 5? Not 5, 125, which is 5 cubed. Now again, we just applied the log properties, but now I'm dividing the 3 squared by the 5 cubed, so this would be using the quotient property, the log of 3 squared minus the log of 5 cubed. And this is equal to 2 log of 3 using the exponent property or the power property minus 3 log of 5. Now, sometimes people think that their answers don't make sense here because they're so used to often getting positive numbers. If you actually do the log of 9 divided by 125, you will get a negative number. And if you think about that, that makes sense. Just think about what the graphs look like, and I'll just do a rough sketch of a graph here of a logarithm. Remember, a logarithm has an x-intercept of 1, and then it looks like this. And we know that the range goes from negative infinity to infinity, and so 9 over 125 is clearly less than 1, and so that's clearly going to be here below the x-axis, which is going to be a negative number. So in fact, if you do the log of 9 divided by 125, you get negative 1.142 going on forever. And again, you could go back and verify, and I encourage you to do so, that if you plugged this into a calculator and this into a calculator, you'd get the same answer. And actually, it's kind of good to do that to make sure you know how to use your calculator, because if you get two different answers here, that means you're not using your calculator properly. So that's not necessarily a bad idea to check just to make sure you're using your calculators properly. All right. Now let's look at one more example here. So we're going to want to find the exact value of the log base 4 of the cube root of 16. Without using a calculator. I mean, we could use a calculator to verify the answer in the end, and maybe we'll do that at the end here using the change of base just to remind us of the change of base. So we're supposed to find the exact value of this logarithm. Well, we're going to have to do a couple steps here. So first off, I'm going to write this as the log base 4 of the cube root of, well, 16 is 4 squared. Now it's also, 16 is also 2 to the 4th power, so why would I choose 4 squared versus 2 to the 4th power? And of course the reason I choose 4 squared is that I've got a base of 4. And remembering that logarithms give us exponents, and we also had a property here that if you, well, it's actually just from the previous videos dealing the introduction videos on logarithms, that if you have the log base a of a, this is equal to 1. So if you had the log base 4 of just 4, that would just be equal to 1. Now, what are we going to do here? Well, I can't still do this, but remember I said you're going to want to get comfortable, I've mentioned this a couple times, of switching between radical and fractional exponents. So this would be the log base 4 of 4 to the 2/3 power. Now, it's very useful to be able to switch between radical and fractional exponents, and again, if you go on and take a class in calculus, this ability to switch between radical and exponential form is going to be critical when talking about a concept called derivatives. Alright, so then let's use some more log properties. Well, this exponent I know can just go down in front here, so this is equal to 2/3 log base 4 of 4. But then we know that the log base 4 of 4 is just equal to 1. So this is 2/3 times 1, which of course is just 2/3. And apparently it's telling me I can update Adobe, which I don't care about. Alright, so then the exact answer without using a calculator is just 2/3. Now, as I said, let's go ahead and do this using the change of base formula. So we have the log base 4 of the cube root of 16. Now you know I like to use the natural log a lot, so this would be the natural log of the cube root of 16 divided by the natural log of 4, because that's the change of base formula. So I'll write the decimals out, even though again we shouldn't. We should just do the computation directly without doing any kind of decimal expansion, so that we can get all of the exponents taken care of. But what we'd have here for the first one here, we would get that this is 0.924196 going on forever, divided by 1.38629 going on forever. And so then if we actually divided those two things, you would get that this is equal to 0.6 repeating forever, which 0.6 repeating forever, of course, is 2/3. So yes, using a calculator we got the exact same answer, which again we should, because we're using properties of logarithms. But we can use properties here to get the exact values. Now again, you might say, well, why would I do that? I could just use a calculator. From a practical standpoint, from computations, yes, you would just use a calculator, and maybe you wouldn't do these this whole properties here. But again, the point of this is really to give us some practice with these logarithm properties, so that we can start applying them to expressions and then later on into equations. So the next video is what we're going to cover that. We're going to do some more examples, but we're going to do examples now with algebraic expressions using the log properties.